Do you remember how you made your first steps? Probably not because you were too young, but I'm pretty sure that your parents held your hands as you made your first attempts. Today, we will see how we can hold the hands of the computer so it can take its first steps. Welcome back to the Applied Deep Learning course. Today we're going to take a look at a super exciting area of machine learning, which is reinforcement learning, and learn about how deep learning has brought a new wind into this field and what cool things you can make with it. Reinforcement learning can be defined as learning how to make good sequences of decisions. Now let's break it down. So we initially don't have any knowledge and we want to learn what positive effects we can get and what steps we have to take to get to the desired outcome of what we want to achieve. Good sequences always refers to some utilization function. So unless we measure our actions in some respect, we can't say whether a decision is good or not. So there always has to be a utilization function which says, okay, this action or this state that you're in is desirable. And it's not just a single decision, but always a sequence of decisions that leads us to that. Imagine that you're a toddler and you want to eat soup. You want to learn to eat soup. Well, then your utilization function would be the amount of soup that you manage to get with the spoon from the plate into your mouth. And it's not that you miraculously will be able to perform this task from one day to the other, but you will try, you will fail, and ultimately we learn how to eat soup with a spoon. There are a bunch of classes of learning problems. Some of them we've already talked about before. The first class of learning problems is so-called supervised learning, which is what we've done most of the time so far. Whenever we're doing image classification or object detection, what we have is our data, which consists of the input itself, X, and the target label Y, which we want to map to. So the goal would be of machine learning now to take X and learn this mapping function that takes X and maps it onto Y. For example, we show it an image of an apple and it learns to say, this thing is an apple. The second class of learning problems is so-called unsupervised learning. And it's related to supervised learning, but there is one thing missing that you will notice immediately. There is no target label Y. So we only have our data and no one is telling us what we should map this onto. And what the goal then would be of machine learning in unsupervised learning would be to learn some structures of the underlying distribution of our data. For example, we show it images of apples and it learns that, well, these two things are similar. They have the same shape, so probably or likely they are the same object type. But maybe the color is different, so on one axis, one dimension that it learns, it would put them close together because they're both apples, and on another dimension it would say, okay, this one is green, this one is red, so I'll put them far apart from each other because they have different colors. That would be unsupervised learning. And the third class of learning problems that we're going to take a look at today is reinforcement learning, where we have state-action pairs. And the goal of machine learning in reinforcement learning is to maximize the future rewards over many time steps. Staying with the apple example, we want to learn to eat this thing because it will keep you alive. We need to eat something, and by the way, apples are healthy, so this should give us a high reward when we eat this thing, which is an apple. There are some challenges in reinforcement learning that it shares with other machine learning challenges that we've already seen, but some challenges are quite unique. The first thing that it shares with what we've seen before is optimization. We also want to get to a low loss. We want to try to make good decisions. And in our case, this decision is measured with a utilization function. So we want to take the sequence of decisions that yield the best outcome that we can possibly achieve here. Or at least you would like to have a strategy which brings us close to that best outcome. The second challenge is the one of delayed consequences. So whenever you take actions, the rewards that you receive from that action might be received long after you've actually taken that action. So, you take an action now, you go to bed, but only 8 hours later you feel refreshed. So one of the most challenging issues with these delayed consequences is the so-called credit assignment problem. What is the credit assignment problem? When you have a sequence of actions, it's very challenging to determine which exact actions led to this positive reward. And because in that sequence of actions that you took, there might be a whole bunch of actions that did not bring you closer to your goal, but you took them anyway because you had to take them. For example, imagine that you can either listen to this lecture now or play a computer game. Well, one of these things will give you immediate reward, the other one probably, or maybe not. Let's see. Hopefully both of them will give you some reward. So when you think about delayed consequences, one really problematic issue is that if the agent performs well, so if you're doing quite well for some time, but at the end you're failing, what we would do is that we kind of say, don't do this again, because you failed at the end. However, everything that we did up until the point where we made a poor decision was good. And now this credit assignment problem is kind of really challenging to say, okay, that subsequence initially was good, we should keep it, we should redo it again, and only from that point in time where we degraded, we should do something else. So that's really challenging to do here. Another challenge is exploration. We're trying to learn how the world works by trying and exploring and often failing to do the intended goal, to achieving what we tried to do here. And one of the biggest issues with this exploration is that the environment that we're operating in often is only partially observable. So we only see part of the environment, and we only ever get rewards for actions that were actually taken. So whether you take the red pill or the blue pill, you don't know which rewards you would have gotten from the other thing, because we only have one life. You can take it and then observe what effect it has. You can't predict the future of saying, okay, if I had taken the other thing, what I would have received. So we actually have to execute our actions in the environment to learn the effects of it. And sometimes exploration has an issue that it never finds a good solution. So you're wandering around, you're trying to find good solutions, and you never get to any point where you perform your task that you're trying to achieve reasonably well. And the fourth challenge for reinforcement learning that is specifically tricky here is generalization, where we try to generalize from something that we already know to something that we have never seen before. So when you think about reinforcement learning, it would mean that we want to have a set of rules that tell us how to operate and which thing to do at each time step, even if we've never seen the situation before. And pre-programming this kind of all possibilities of actions that I can potentially take is very often untractable. So we have to find other means to generalize well. And machine learning is obviously one way of doing this. There are a few key concepts and terms that you will encounter all the time, so it's really important that we talk about them at this point so you understand them. First, we have an agent. The agent is the central component. It can be a drone, it can be a figure. In real life, it's you. You are the agent that is operating. And you're not operating in the air, you're operating in a certain environment. So an agent, if you think about a computer game, could be your figure, your character that you're moving around, and you have this virtual world. If you think of simple board games, the agent would be the player and the environment would be the chessboard with its figures. And you as an agent can take a move in that environment. Which brings us to the next thing. You can take actions. And the action has a certain time step. So your action happens at a particular moment in time. So we would say it's the action A, T, at the time step T. And whenever we take an action, we are able to observe the environment back and see how the environment has changed by saying, okay, now what we can see is the state in the next time step. So the state as t plus 1 after we took an action. So we moved the bishop and now we see a new state in our chessboard. And what we typically also get back from the environment is a certain reward. So whenever we take an action, we will have to determine according to our utilization function whether it was beneficial to us or not. So that's the reward. And as I said before, the reward that we're getting here, just to make sure that you don't get confused, the reward is also based on a time step, but you might not have an immediate reward, but there could be delayed consequences, so the reward that you're actually getting could happen much later after you took an action. Another key concept is the so-called total reward. So the reward that we get from each time step, we can basically just sum up all the rewards that we are seeing into the future. That sounds a bit obscure, but think about the following. When you play a game, what you can do is you can just record the game. And once you've recorded the entire game up until the end, you can determine the reward for each individual step. So maybe you beat some other figure in the middle of things, so you receive a reward for that. Or if you think about Pac-Man, you're moving around, you can eat these coins or these small things along the way, these breadcrumbs, and they'll give you rewards on the way. And then you can just sum it up, all of these rewards. It's always depending on your environment and your task, but you can just build the sum of all the rewards that you will see into the future from starting at a certain time step. One of the problems is that given a potential unlimited time series, that total reward could get infinite. So we're just adding more and more and more rewards. So what we can do instead is add a discounting term, a discounting factor gamma, which decreases the rewards that we're seeing over time. So whenever we get an immediate reward, we have a higher value here, a higher discounted reward, as opposed to rewards that we're seeing far into the future. And depending on this discount factor, we can adjust how much we want to be gratified for things that happen in the future or immediate rewards. Just a quick side note, if you have issues with procrastination, it's probably because of this discounted total reward that is going on in our brain. Because I love this term, I came across it recently, which is called the instant gratification monkey that we all have in our brain, which says do something that gives you immediate rewards. So if you play a computer game, that will give you an immediate reward because the computer game is designed to give you this reward, whereas listening to this lecture will give you a reward maybe later when you complete your project and you're really proud of what you've achieved, or when you're at work in maybe some time in the future and you can profit from the knowledge that you've gained here. But your instant gratification monkey will always drive you to do the things that give you instant rewards. That's why we tend to do things and procrastinate sometimes. But just a quick side note. To the last few key concepts that you should really be familiar with. The first one is the so-called quality function. The quality function, or abbreviated Q function, you will see all over the place. It's the reward that you can expect when you perform an action A in state S. Quite clear? So we say we're in state S. What reward can I expect when I take one particular action? The second function that we're discussing often is the so-called value function. The value function is kind of the average reward that we're expecting when you're currently in state S. It just evaluates, so it's not bound to a specific action, but it just says you are in state S, how good or bad is that state? What reward can you expect on average when you are in this particular stage? And think about a chess game. You can have a position where you're likely to win and then you'll have a high reward here, or you can be in a state that is poor where you're likely to lose, then the value function will give you a low value. And the third thing here, which is from this broad category, is the so-called policy function, which is the oracle. The oracle that says you're in this state, you should take this action to maximize the rewards that you can receive. So it's a probability that a certain action A is the best option in your state S. Given these functions, we can actually compute or design one more function, which is called the advantage function. So given the quality function, which says the given state S, how good an action is, and the evaluation of the average of that state, the value function, we can compute the difference between these two things, which tells us how much better the action A would be compared to the average actions that we could take from this state. One of the hardest things about these functions is that in theory, well, they all make sense, but it's really hard to come up with these functions and kind of design them for your problem to work really well. We've actually already seen one of the value functions when you think back of the first video in the first lecture. That's not the first video, but the video in the first lecture where I showed you the computer being able to play StarCraft. And when you take a look here at the right bottom here, the outcome prediction, there you go. This is pretty much a value function in the sense that they evaluate the state that the machine is currently in. So it considers the number of units it has, the terrain it explored, the resources, how many enemy units there are, and out of this it tries to predict whether it's likely to win or to lose. So it's kind of the value that says at this state that I'm currently in, what are the chances of me to winning or losing? If you have a Q function, if you can magically come up with a Q function for your problem, how would you get from that Q function, which says a particular action in the state gives the highest reward, to that action? So given the discounted total reward, you can say, okay, the Q function captures the expected total future rewards an agent can achieve when taking an action A in state S. So it's the expectation of this total discounted reward. And when we have such a function Q, that is the expectation of this total reward, what we can do is we can say, okay, a policy function to say which action I should actually take is basically just taking whatever action gives us the highest reward. So we take the argmax of Q given a certain state. And that is the simplest way how we can get from the Q function to an action. By kind of reformulating it, it has a simple policy that gives us a particular action. And reinforcement learning, the biggest challenge is to find such a cue function or a policy function. Let's talk about deep reinforcement learning, and what we've seen so far was mostly the overall and basic ideas about reinforcement learning. So let's see how deep learning made a twist in this. Deep reinforcement learning algorithms are typically divided into two broad categories. One would be value learning. We're trying to find exactly this cue function that I've just been talking about. So we're trying to learn the cue function somehow, and given a cue function, we can take the policy that we've just said of taking the argmax A, the action that gives us the highest reward in each state, and applying that. Whereas a policy learning function, policy learning algorithm would say, okay, please directly learn the policy which says which action I should take. So we learn a probability distribution of actions, and then we sample from that probability distribution, which, if it learns the perfect underlying distribution, which always says which step to take, it will give us the perfect outcome. Deep Q networks are one family where we see how deep neural networks and Q functions play together. So how this works is that we have a deep neural network in the middle, and what we feed into the neural network is the state S, all of the environment variables that we can observe, and the potential action that we can take. So we start with the first action, move right in this game here, and it will give us the quality, and it should learn the quality function that is the expectation of this total discount reward that we're about to see in the future. One thing that, when you think about this architecture, it's quite costly, because for each possible action that we can take in our environment with our agent, we have to run it through this network. So we can make a better job here by reformulating the problem and only feeding in the state S through our neural network and predicting the Q functions for all potential actions that we can take at the same time. Therefore, we only have to run through our model once. One thing that you'll realize here, this only works for if we have a discrete set of actions that we can potentially take. So how do we learn this thing? The Q function is a function. And what machine learning models and neural networks do, they approximate functions. So it kind of makes sense. And when you think back of the parts that we need to train a machine, you need a model, you need a loss function, and an optimizer. We already know how to optimize this. So we just need a loss function really here. And we can take the mean squared error between the result that we can observe at the end when we play the game and the prediction. And ideally, we just want to have very similar functions, to have the loss, the difference between what the network predicts, what the future reward will be, and our actual reward to be as low as possible. So we just use the mean squared error here. The right part here, Q of SA, would then be the predicted output of our network model, and the left thing would be the target. How do we get the target? We play the game, we record all the steps, and afterwards we can just compute this, because we know the rewards that we've seen until the end of that game. Deep Q networks work exceptionally well for a wide range of problems, and they've been shown to work also really cool and really good for Atari games. So if you're a fan of these old Atari games, you will be delighted by learning that computers can play them quite well. Most of them even better than humans. So how do they work? They have their input is the game board. For example, the actual image of that game board. You use a convolutional neural network to extract features and to learn what the specific things mean in that network, and then you have a classifier in the end. Because what we ultimately want to output is an action that the neural network should take. So it's a classification problem, and we already know how to do classification with neural networks. So you can have a couple of fully connected layers in the end, and then they predict which action you should take at each time step. And DeepMind, they have been working on this for a long time now, have shown that it works for a wide range of situations. And for the left part here, what is also quite interesting for you to know is that you can use all of the existing knowledge that we've already gained. So you can use a convolutional network, you can use recurrent network, you can use combinations of these depending on your problem. If you think it would make sense to have some sort of memory back to what you've seen before, then use a recurrent neural network. If you don't think that remembering the past is that relevant, you don't have to use it. You can just use a standard convolutional neural network if you have images. Or just use a fully connected layer if you have maybe time series or other things where you don't need to have that grid-like input. This is the overview of Atari games that they trained on. So we can see that there is a wide range of games on the left of this bar here, which says at human level or above, like boxing or breakout, the game where you have moved the paddle and you have to kick blocks at the top. So at these games, the computer can play exceptionally well, even better than we humans can do. And there is a threshold where it performs worse. You might ask yourself, what is the reason that it performs better in certain situations and worse in other situations? That is a really interesting observation, which is the keyword which brings us to the reason: observability. The computer can perform really well if the environment is fully observable and it sees everything that's on the board and can use that knowledge to make a decision. However, if the environment is only partially observable, or the rewards are being received very late in the episode, in the game that we're playing, the computer has a really hard time playing this game. One example here would be the end of this thing here. You can see Montezuma's Revenge, which is a jump and run game where you have to jump around and find a key, and then with that key you can, I think, open a chest or something, and that wins the game. So most of the actions that the computer takes will not see any rewards up until the point where it actually wins the game. So it tries so many random actions and fails. It falls down to the floor or gets eaten by the monster that is flying around, that it virtually never manages to get that key and open the chest or open the door. I'm not sure what the goal of the game is, but it has a really hard time playing that game. There are some downsides of Q-learning, so we can only handle limited complexity. So modeling scenarios with large or continuous action spaces is not really possible, because think back, we have a discrete output of actions that we learn to predict with our Q function. If that is very large, we have a very difficult classification problem because we have so many potential outputs that it's hard to make a good decision here. What you can do if you have, for example, a continuous action space, like think you're driving, working on a self-driving car and you're adjusting the steering wheel. Of course, that is a continuum that you can position the wheel, the steering wheel, but you can just discretize this and just say, okay, I have maybe 20 or 30 discrete steps where the position of the wheel can be in, and then you're saying, okay, please give me one of these 30 possible outputs, and then this kind of problem becomes handleable. It's also, in terms of flexibility, Q-learning is a bit limited as it cannot learn stochastic policies, because the policy is deterministically computed from the Q function. We know how we get from the Q function to the policy by just taking whatever action gives us the highest reward. And if their next state has a random component that means it's stochastic, we cannot handle this stochastic process with Q-learning. So what can we do instead? We can, with Q-learning, we're learning to approximate that Q function and then infer the optimal policy by always taking the maximum, the action that gives us the maximum reward. But we can also directly learn the policy, and that will be called policy gradient, where we try to learn the actions that we should take in whatever state we are. So we again feed the state into the deep neural network, and what we try it to learn is the policy of potential actions given that state. We're basically learning what is the correct action to take instead of saying which action gives us the highest reward and then taking that action. Do you see the difference between these two? I hope you can see the difference in these two functions. So how do we train policy gradient? Can we achieve such a thing? First, we run this algorithm. We run the policy for a while. If you think of the game Pong, you have this paddle, like two paddles that are moving up and down, and the ball goes back and forth, and you can either move up or down or not move at all. In this case, you can only move up or down, and you record the sequence. So the ball goes back and forth, and ultimately it hits the wall behind one of the paddles, and you win or you lose. So that will be the reward. If you win, you get a positive reward. If you lose, you get a penalty. So we run the policy, whatever initially we've come up with, for a while, and then our learning process would try to increase the probability of all those actions that led to a higher reward and decrease the probability of all those actions that gave us a low reward. Sounds quite obvious, I think. So how does this look like in code or in pseudocode? The function reinforce goes in the following way. We initialize our model parameters, our policy, and then we run this policy. And each run here is called episode. So whenever we start our agent in the environment up until the point where it terminates, either because we win the game or we lose the game, or we just say stop at this point, that is what we call an episode. So we can have a bunch of episodes that we're collecting, and if we ran this 4 times and learn on these 4 episodes, we can group them into a batch of episodes. So each episode is a collection now of state, action, reward pairs, because we knew the states that we passed through, we know the actions that we've taken and the rewards that we're seeing ultimately. Now what we can do is we can update the parameters that in the following ways. So we compute the gradient here by multiplying the log likelihood of a certain action in a particular state with the expected discounted reward. So the left part here, the green part, would be the log likelihood of the certain action in a state, multiplying with the expected discounted reward from that point in time. So that is our gradient, and we can compute the backprop step here. And once we have like our update, our gradient, we can update our parameters with the gradient in the same way that we've already seen it before. When we're training reinforcement learning, we can apply the so-called greedy exploration or epsilon greedy exploration. So you can start, or you can basically do 2 things. Either you just take a random action in your environment, which would be the exploration phase, where you do whatever you want, walk in a random direction and explore different areas of the environment that you maybe haven't been before. And you can say, okay, there is a certain probability epsilon with which I will go this path and just take a random action. And the second path you could do is exploit the knowledge that you've already gained from previous learning phases and say, with a probability of 1 minus epsilon, we pick the top action of the policy. And the way how you can train now is by reducing that epsilon, so starting with a pure exploration, setting the epsilon value to 1. So we only take random actions, and over time we reduce that value of epsilon until we end up at a point where we only follow the policy and do not take any random action anymore. But by doing this greedy exploration, this epsilon greedy exploration, we can find a good balance between exploring our environment, exploring new ways to solve the problem that we're tackling, and making use of what we've learned before. When you think about the rewards that we're getting from our training, we often have an issue that we only get sparse rewards. We might only get rewards at the end of the episode. So the natural idea would be now, if we have this issue that we're only being ever rewarded at the very end, we can potentially incentivize the agent to go into that direction if we give him something along the way. The idea would be to shape the reward in such a way that the agent receives more rewards along the way. So we can design more mechanisms that produce these more frequent rewards, and by doing so it becomes easier for the agent to converge to the solution that we wanted to go to. The downside of reward shaping, though, is that it's a custom process that needs to be redone for each task, and we have an alignment problem. So when you shape the reward function, it might happen that the agent finds an interesting or funny solution which maximizes the reward from the thing that you shaped it to do, but that did not end up doing what you initially had in mind and that you wanted it to do. So one quite fun example from a student from last year was he was programming an agent that was moving around in a game terrain. I think it was a chameleon that was learning to eat flies and avoid rocks. So it was moving around, and whenever it found a fly, it got a positive reward. When it hit a rock, it was penalized. And the issue was that the agent was always bumping into walls. And he didn't want the agent to bump into walls. So what he did was he added additional rewards, in this case an additional penalty if the chameleon hit the wall. So it would kind of prevent the chameleon from constantly running into these walls. And what happened? Instead of avoiding the walls and just walking away from it, the agent became paranoid. It became so terrified of walls because the penalty it received whenever it bumped into the wall was so high that it stopped moving altogether. It was just standing still, and it didn't do anything anymore because that gave the highest reward to the network, like 0, which is higher than all of the negative rewards that it learned when it bumped into the wall. So you can see from this example that whenever you do reward shaping, you might end up with this alignment problem that the network might learn something that's surprising and that you did not have in mind initially. And finally, it limits the solutions of these rewards to what we can imagine and what we can come up with. And if we don't dream up better rewards, the network is lost here. So instead of shaping the reward, we can also just add new tasks. And some of these auxiliary tasks, how they call them, can be supervised with what we design to give additional rewards, or it can be unsupervised. And this is a really interesting example of the second category of unsupervised auxiliary tasks that we don't have to shape in some way to say, doing this gives you that reward, but the agent is just incentivized from these tasks. So the game that they're playing here is that you are walking around in a three-dimensional maze, and your goal is to pick up these apples and objects. And what they're doing is they're adding 3 additional rewards. The first would be B here, which is the so-called pixel control. The pixel control learns to maximize the change of pixel intensity. Why would you learn to change the pixel intensity? Well, whenever the pixel intensity changes somewhere, so you take a turn, you are moving. You are going somewhere where you haven't been before. If you're standing still, intensity of pixels will not change. So that additional task here will incentivize the agent to move around and explore places where the background changes, where the image changes, where it sees something that it hasn't seen before. The second thing that they add here on the right bottom is the reward prediction, where given a few frames from the past, it tries to predict the reward it will get in the next step. So it saw the last few steps, say, okay, what is the likely prediction that I'm going to see in the next step? And the third reward the third task that they're adding here is a so-called value function replay, where you're trying to predict future rewards starting from a state S. So let's take a look at how this looks like. So the agent is moving around, trying to pick up some objects, apples or lemons or whatever that is supposed to be. And you can see it's doing a pretty good job. Eventually it runs into these funny objects that teleport it to a different place. So yeah, these red funny shaped things. And it's doing a pretty good job, so it's exploring the world and moves a little bit shaky to the left, to the right, but it doesn't hurt too much. And it can also learn to do other tasks like shooting this laser, and yeah. Now comes the interesting part where they visualize what those auxiliary tasks internally contain. So you can see the pixel control on the right. The pixels that change intensity are kind of the sky and some other parts. You can see the reward prediction. So at the right half of the image, you see that whenever it eats an apple or is shortly before eating an apple, it kind of predicts whether it will get a reward or not. And at the right bottom, you see this value function replay, where kind of the value that it predicts, the reward, goes up and down. Another interesting technique is so-called curiosity-driven exploration. You can extract features from the current frame into a latent space. Why would you do this? So between the thing that we can observe and the things that matter from our environment, that mapping would be learned from extracting features. So this allows the network to say, okay, what of our environment is relevant and what is not. It's learning this mapping from the current frame into this latent space. And given latent space representation for the next frame, the forward network tries to predict the same latent representation. So let's take a look at the figure. So that is our agent here. We have policy, which takes an action, and we move into the next state. And this is the interesting part here. So we have the state S at the time step T. We can extract some features. And we have a forward model, which tries to predict, given the representation from the last state and the action that we're taking, the same representation of the next time step. And then when we roll out the policy and play the game, we actually know that feature here as well, that representation. And what is the effect of having both this latent space representation of the next state and predicting the same thing? Well, that way what happens is that when the agent is in an environment where it has been before, the prediction of the next state will be quite accurate because it has already seen this before, so it knows how the environment will look like a little bit into the future. Therefore, when we take now the difference between these two things and use that as an additional reward, we will see that if it has already seen this before, the reward that it gets from this component here will be low. And if it is in an environment that it has never seen before, it will do a really poor job at predicting the next state. So the difference between the actual latent representation of the next state and what the network predicts will be high. So it will drive the agent and reward it for exploring unseen parts of the environment, which is a really interesting thing to have, and it really can help your agent to perform much better. So it kind of saying that getting your agent to intrinsically explore the environment is a crucial part and can really help you in many settings. One more thing that you can see here is the so-called inverse model, which is also an interesting idea. So what you can see here is that given the latent space representation of the state st and the latent space representation of the state st plus 1, the inverse model learns to say, okay, so we were in that state, now we're in this state. What was the action that we took to get from that state to the next state? And what this really helps with is the following. If we extract meaningful features from our environment, we can actually learn with this inverse model to it helps to distinguish all of the environment variables that were relevant and that we could influence with our actions and distinguish them from everything that we don't have any control over. Because the state change, if we don't have any control, will be independent of our action. So if we predict the inverse action that has been taken and there is a causal effect, causal dependency between the state and our action, we will actually predict this here correctly. So we'll learn this and therefore ultimately learn which parts of the environment are relevant for us and which are not. Another really interesting idea is the hindsight experience replay. If you have an imaginary robot arm that you put in charge of moving objects around or kicking, and it's flying a little bit and it should end at a certain position that you want it to end. The problem is that when you train this for the first few episodes, it will perform very poorly. It will throw it somewhere, but probably not where you want it to land. So what happens? It fails, so no reward. What we can do now is pretend that wherever the object landed, it was not where we initially wanted it to land, but we can pretend and say, I wanted it to land exactly there. This is exactly what I ever wanted you to do. And we create this virtual goal. So the goal here in the image is that part here, but it actually landed here. That's the outcome. So what we say, we define this part here where the object landed as our virtual goal, and by saying that is our goal and pretending that is our goal and changing our goal on the flight, we can say, okay, I can give you a reward because you did exactly what I wanted you to do. And one really positive effect of this is, apart from having more rewards for your machine, that once you get to this point where you want the arm to move the object to that location, it has already seen it before. it already pushed it there once, so it had some learning for that action. So this is a really interesting technique that can help you accelerate your learning. Some of the practical reinforcement learning tips that I can give you along the way. First of all, the OpenAI Gym, which is a great toolkit for developing and comparing reinforcement learning algorithms. It contains a really clean way of training reinforcement learning environments. It has some built-in environments, for example, for all these Atari games, which makes it really easy to train and play around with it. And I would actually go that far to say this OpenAI Gym is kind of the MNIST playground for reinforcement learning if you want to try out a new algorithm or a new gradient policy or something along the way. How does it look like when you do something with OpenAI Gym? That is a short example here, how you can play Pac-Man with this. So you say import gym, you make the environment where you specify Pac-Man as your environment. You reset the state to the initial point where Pac-Man is in the center and the ghosts are somewhere around. You say, well, not done yet, and you initialize the total reward to 0. Now, until we're done, so until either the monster has eaten us or we've captured all those coins or bricks along the way that give us some reward, we're playing this. So what we do is we render it, so we kind of display it. If we don't want to render it, then we don't need this command. And then we sample from our action space. Our action space are all of the actions that we can take, like go left, go right, top, bottom, up, down, or stand still. Maybe if that is also possible. And the easiest way how that would play here is just take a random action. So we just sample from those possible actions, and then we apply that action in our environment. We take a time step in that, and that time step gives us a new state that we are now in, potential reward if we've found one of these things that give us something, and it also says whether the game is over or not, and until the game is not over we can repeat that in a loop, and if we receive any reward we can just sum it up to see when we and kind of remember this, the memory of when we received which reward. This is an interesting example of how you can play Pong from pixels, and we're going to take a look at the code now, how you can use a very simple neural network to learn to play Pong from the pixels, from the raw pixels. Okay, we're now in our code, and what you can see here is that we're initializing a few parameters, so we're setting the number of hidden neurons in our hidden layer. We're saying how many episodes of the game it should play before we start learning, and some more parameters here. And then there is the model. So it's a really simplistic model, which is just 2 weights. And in the forward pass, when we go forward, here you see how they're being computed. So you take the model, you multiply it with your input x, you do a ReLU, nonlinearity, which is super interesting to say just, okay, whatever is below 0 is 0. So that's a ReLU activation in its most simple form. Then we apply a second multiplication and apply a sigmoid function. And that is our probability that we're seeing as the output here. What else is here to see? They also do some pre-processing to kind of only take a look at the relevant parts of the game board. Here they show how to compute the discounted reward by running over that memory of rewards that we got along the way in the reverse order. There is the backward pass, how we can backprop, and here is the actual thing that we've been waiting for. So we create the environment, we reset it, and here in this loop, we render it, and then we can observe so here is the policy forward where we kind of run our action, and I think it's doing some random actions here at the beginning, and eventually here it will take that action that we've decided on taking, and we're getting some rewards back, done, info, and so on. And if an episode is finished, so if we played this until the end, until the game, like the ball hit the wall, we can now do our policy backward step and compute the gradient and do all those nice things. So let's run this short program and see what happens. So that is our Pong program. As you can see, it's not doing very well because it has just been initialized with random values. Eventually it will hit a ball, possibly only by accident. Let's watch a little bit longer. I think eventually after some time it will be lucky enough to hit the ball once or twice, so it goes into the enemy's wall. Yeah, it's doing a really poor job at the beginning. But as you can imagine, after a while it will do this, and I leave this as a playground for you to run this small example on your home computer, maybe add a few more layers or play around maybe with a convolutional network and see if you can change this. And of course, all of this code that you're seeing here, they manually did the forward pass, the backward pass, the model computation. So if you try to achieve the very same thing with a deep learning model, you can probably get a much smaller code base while you just compute a few steps with PyTorch, for example. And you can just say backprop and it will do everything for you. Another reference framework that I find particularly useful for reinforcement learning is RLPyT, which is a modular implementation for deep reinforcement learning in PyTorch. And you can play around because they already implemented many of the algorithms that are really popular here, like policy gradient or deep Q-learning that we've seen before, and a lot of other functions and algorithms that belong to this family of reinforcement learning. And you can learn a lot about reinforcement learning from this, and by sticking to this framework that they are giving you, it can also help you to guide you. And just take a look at some of the examples of what they've done before to learn more about how to do this. If you want to learn more about policy gradient algorithms, I'm pretty sure that there are many new algorithms coming out on a regular basis where people have great ideas. We've already seen the reinforce algorithm, but there are, as you can see here, almost 20 different algorithms that are just described in this single article. Check it out. It's really interesting to learn how the evolution of these different policy gradient algorithms are and what ideas went into it and how they designed it to add more information and find ultimately a better policy. Spinning Up Reinforcement Learning is also a very excellent resource that I can absolutely recommend, where they have a good summary of tools and background information that really helps you to get started with reinforcement learning. It's a great resource that you should definitely check out if you are doing a deep reinforcement project. If you're not doing one, you can check it out anyway. It's super interesting to take a look there, but bring along some time because you will want to continue reading and exploring what is on that website. A few interesting examples of reinforcement learning that we've already seen come from DeepMind company that now belongs to Google. And what they did in 2016 was remarkable. They managed to train a machine to play Go, and not just to play it in any way, but to play it so well that it beat the world champion in Go. Their program was called AlphaGo, and they trained it in the following way. They started with initial training of human data. So they had experts who played the game, and the machine saw those replays of the games that the human experts played and tried to mimic their behavior, tried to become as good as the human experts in these games. And once it got to a certain point where it fundamentally understood the game and was reasonably well playing, they copied the model, and then they had two copies, and they let those two models play against each other. And the good thing of the self-play mechanism is that whenever you have two opponents, one of them is bound to win. And when you win, you have a positive reward. So you did something wrong, and whatever the loser made wrong, you can also learn from that and get a negative reward. And therefore, you can self-train that network to become better and better in this game. And the third step, what they did was they learned a value function, a value network, that takes the status input and outputs the maximum Q function. It's kind of this Q function for each state. And if you have a value function, think back of what a value function is. It says which states are desirable and which states we would rather have to avoid. We should rather avoid. It tells us which states are desirable and which states we should rather avoid. And the value network is also used to prune itself in an intelligent way. So if the network knows that a certain state is undesirable, it will stop executing actions from that branch. So if we're already in a really poor state, why should we simulate anything else in that state? We'd rather try to find a different path in our network. And in 2016, they beat the top human Go player, so the world champion in this game. And why it's so particularly remarkable? Because the game of Go has a really complex state space. It's super large in terms of possible states that the board can be in. And did they finish there? No. They got really curious and thought about, well, how can we get even better? And can we use this framework that we're used now to train Go for something else? And it turns out, yes, you can use the same ideas. So what they did in 2018, they published another work called AlphaZero. And instead of having the humans pre-train the network with experts, the framework just learns everything from scratch on its own through self-play. So you have the rules, you have two models, and you just let them play against each other. And what you can see here is for 3 different games, chess, shogi, and Go, that if you train it for a certain number of steps, they will become better than the baseline that they're using. So what you can see here is this ELO, the rating system, which is a relative skill level for players in zero-sum games. And it postulates that each player's skill can be modeled with a normal distribution with a certain center. And when 2 players have the same rating, they are likely to win for the same amount of games. And what you can see here, of course, Stockfish, I think, is a chess robot, a chess machine, a program that has a certain number. And after a while, it consistently was beating that computer game, that computer program. And you can also see that for other games that AlphaZero was consistently beating whatever they've trained before. This is a really interesting quote that I don't want to hold back from you. The world champion said, Demis Hassabis playing style feels alien. It sometimes wins by offering counterintuitive sacrifices, like offering up a queen and bishop to exploit a positional advantage. It's like chess from another dimension. And this might sound scary, But it's really remarkable to see that the computer learned to go into certain directions that were so out of our realm of imagination, but eventually got to a better solution than we could come up with. 2019, I would say, was yet another milestone in this evolution of what DeepMind achieved. And what they did is they were able to train a machine to play StarCraft 2, which is a real-time strategy game where you move figures around, you build up your base, and you have to defeat the enemy. And internally, they used all sorts of nice things that we either have covered already or that we'll cover soon, like transformer networks, LSTMs, pointer network, and some other mechanisms. And they were able to beat also really world-class champions in this game. One video we've already seen was against this streamer Mana, who's one of the world's best players in this game. And the network was able to beat him consistently. I think only one game the player won, Mana, and he exploited some bug where it kind of lured the enemy to go up and down, follow one unit, and while that computer was following the player's unit, it was able to destroy the enemy base and therefore win the game. But it was, he also described this as a kind of super extreme challenge, and that the computer was extreme, for example, in its micromanagement, that it kind of controlled each individual unit. And to make the game somewhat fairer, we have to acknowledge the fact that the computer can potentially do many clicks per second. So what they did was they actually restricted the computer to also only be able to, I don't know, perform 60 actions per minute. No, I think it was more, but like maybe 200 actions per minute. So you can kind of click 3 times per second, which I think is roughly what professional players do. They have a really high speed on moving around, taking a look, and then controlling the units in their game. But still, I think it's really remarkable to see how well their computer performed here. One funny detail at the end here, they said that when you compare the amount of games that the machine has played against itself, it would correspond to a human playing time of 200 years. So if you played StarCraft 2 for 200 years, you better be good at this game. Summing up, reinforcement learning is a class of problems that operates on this state-action pairs that we've seen, where we have an agent in our environment and we perform an action in that environment, and then we can observe how the state of that environment has changed. The common functions that we're talking about and that we want to learn is either the Q function, which measures the expected rewards from taking an action A in state S, the value function V, which measures the expected rewards from that state S, which evaluates how good the certain state S is, or the policy function, which directly says what is the best action that you should take if you are in state S. For deep reinforcement learning, we typically distinguish between value learning or policy learning, where we either want to learn a Q function or directly the policy, and we've seen that we can reformulate this as a classification problem in many cases with deep Q networks to be able to predict certain policy. And there are many challenges along the way. I've only been able to cover a few here, but once you start working with reinforcement learning, you will realize there are way more. Some of the most challenging ones are this partially observable environment that we're operating in, where we have possible sparse rewards or late rewards. So whatever action we take might only have an effect far into the future. And if we don't know which action led to a certain outcome, it can be really hard to assign credit to certain parts of our action sequence that we took. So this credit assignment problem is really, really challenging. And finally, reinforcement learning can be seen as a sort of supervised learning, but on a continuously changing data set. So it's a classification problem, but instead of having the same data set running over and over again, we're seeing different data at each episode. I hope that what I've covered today about reinforcement learning was helpful for your project, and if you're not working on a project, that whenever you come across a really cool new idea, you can give reinforcement learning a go and play around and then use the knowledge that you've gained in this lecture. Stay safe, and I'll see you very soon.